Lesson 11.5 is about sums of infinite geometric series. Now, we already know that a geometric series is it's when you add up all the numbers of a sequence that's geometric in nature. So you're not adding numbers to change going from one to the other, you're multiplying. So let's say we're multiplying by 1/2 and we started at 1. So we'd go 1 plus 1/2 plus times another 1/2 is 1/4 plus 1/8 plus 1/16 plus and so on. And we just continue multiplying by 1/2 each time. So an infinite geometric series would be if we assumed that this pattern continued on forever and we added up all of those numbers together. That would be an infinite geometric series. A partial sum is when you only take just a piece of it. So if we were to only add up these three, that's what we've been looking at before, a partial sum of a geometric series. But now we're going to be talking about an infinite sum of our geometric series. And we would say that if we do have a sum of our geometric series we can take all of our numbers and add them together, then it is called a convergent series. Otherwise, if it did not, it would be called divergent. So let's see exactly how we take that sum, how we find the sums of convergent series. The first stipulation that we need to know is that our R value, the change from one to the other, must be in between -1 and 1. Now it can't be exactly -1 or 1, but it just has to be in between them. So basically it has to be a fraction. Another way to write this would say the absolute value of R has to be less than 1. It's another way to look at it. So the first thing to do is always to find your R value. Then the second thing is to check your R value to make sure that it's in between these values, like we said. I should write check R. The third thing to do is just plug it into our formula. And what is the formula? Well, we'd say the sum of an infinite series, or a convergent series, so one that we know does have an infinite sum, is our first value, a sub 1, over 1 minus R. So it's actually fairly simple. So let's, I want all of these. Move these down here. Let's check this first one and see what our R value is. Remember, to find R, we take one term and divide it by the term before it. So we would take 4 divided by -4/3. Now whenever you divide by a fraction, that's the same as, I'm going to change 4 to 4 over 1. That's the same as multiplying by the reciprocal. So we'd say multiplied by -3 over 4. So we did 4, or 4 over 1, divided by -4/3. It's the same as multiplying by -3/4. So in the end we have -12 over 4, which means our R value is actually equal to -3. Now if our R value is -3, then we know that that is too big of an R value. Get these together, scrunch it down. Our R value is too big, so we would say that the sum does not exist, or we can say there's no solution. This is not a convergent series, so it doesn't work. Well, that was pretty simple then, so let's go on to the next one. See if we can find one that does work here. So we want that R value, we want the change in between those two. So this time it's -3 over 2 over 3. Same thing, we can just multiply by the reciprocal. -3 over 2 times the reciprocal of 3 would be 1 over 3. So in the end it comes out -3 over 6, which is the same as saying R equals -1/2. Now -1/2 is between our values of -1 and 1. So this one does have a sum. Oops. Let's undo that. This one does have a sum, so let's go ahead and find what that sum is. Remember, all we have to do is just plug in infinite sum equals our first value, 3, over 1 minus our r value of negative 1/2. 1 minus 1/2 is the same as saying 1 plus 1/2, or should I say 1 minus negative 1/2 is the same as 1 plus 1/2. So we can either say that it's 3 over 1.5 or 3 over, I'm going to call it 3/2. Makes things a little bit easier to deal with, because then it's 3 over 1 times the reciprocal of our fraction there, 2/3. So then it's 6 over 3, which is the same as 2. So if we were going to take all of these numbers forever, add them all up, they would sum up to 2. So that's how we do it in our basic normal sequence form. So if we know our first value, find our r value, just plug them right in. How do we find that out during a sigma notation? Well, it's going to be the same exact form. We just need to remember where our values are. So remember, in sigma notation for a geometric series, this value here, the one that is to the power of n minus 1, that's our r value. So r equals 1/2. In this case, it's this piece. The piece that comes in front of it, this 5, this is our a sub 1 value. So we would say a sub 1 equals 5 in this case. And again, our sigma notation lets us know we start at our first value, go all the way to infinity. That's how we know it's an infinite sum, because we're continuing on to this value up here, infinity. So we just plug it right into our formula. Sum of infinite amount equals our first value, 5, over 1 minus 1/2. So 5 over 1 minus 1/2 is just 1/2. So we'd say it's 5 over 1 times 2 over 1, which means it sums up to 10. So if we add all of those numbers together, we'll finally arrive at 10. All right. We can use some of our skills at this point to write repeating decimals as a fraction. So if we have this fraction, 0.25252525, repeating as a fraction or as a decimal, and we want to find it as a fraction, how can we convert it? Well, I'm going to write the steps first, and then we'll go through it. The first is to write your decimal equal to d. Second thing we do is multiply by 100. Now, there's going to be a stipulation on this, and I'll tell you when you want to multiply by 100, when you want to multiply by 10, when you want to multiply by 1,000. You'll always be multiplying by a power of 10, but for the most part, we'll just say that you multiply by 100. The third thing to do is take your new equation that you get, and you subtract the two equations. So kind of like during our substitution and elimination forms of solving linear systems of equations, we just line up our two equations and subtract them. Then in the end, the only thing left to do is solve for d. Now I'll show you how these actually work over here. So if we have 0.25252525 repeating, we would say d equals 0.252525, continuing on. So we've written our d. Now we want to write it as a multiple of 100. So we'd say 100 on this side, 100d equals times this by 100, so we move the decimal point over two places. So we would actually say that this is 25.25 repeating. Now we subtract these two. So I'm actually going to move this one down so that we can subtract these two. It'll look like this. So we end up with 99D equals 25.25 repeating. Notice how this piece is the exact same as all of this. So we're just left with 25 then, the piece in front of the decimal point. So now we have 99D equals 25. Now we just solve for D. Divide both sides by 99. So in the end we'd say D equals 25 over 99. And that is how we would write our decimals as a fraction. So how do we know when to multiply by 100, or when to multiply by 10, or when to multiply by maybe 1,000? The decimal point to get to the repetition, it's 25, 25, 25, 25. We had to move over two places, 1, 2. So that means we need to multiply by 100. If our fraction was, say, 225, 225, 225 repeating, then we'd have to move it over 1, 2, 3, and 1, 2, 3 again to get to our repeated form. That would mean we'd have to multiply by 1,000. Now let's say our fraction was 0.888888 repeating on. We'd only have to move it over once to get it to that repeated form, because it's only 8 that's repeating each time. So we could multiply it just by 10. But to be on the safe side, you can always just multiply by 100, as long as it's not one of these ones, because multiplying it by 100 on this one still gets us to a repeated form. It is 88888 repeated, or it could be 88, 88, 88 repeated on and on. So 100 works as well.